In this section, we're going to do some more curve sketching. In the last section, we really just restricted ourselves to curve sketching polynomials. The domain of those functions is all real numbers. And we'll just sort of recap a bit of what we learned there, how we go about that process. And the information we get from derivatives is summarized in this table. The first derivative tells us whether the function is increasing or decreasing. And the values where the first derivative is 0, we call those critical values. And what we do is we check for a sign change in the first derivative using our sign chart, or check the concavity at a critical value to see if that critical value is a maximum or a minimum, or maybe neither. The second derivative tells us about the concavity of the function, whether the graph is concave up or concave down. And the places where the second derivative is 0 are possible inflection points. We have to check the sign chart for the second derivative for a sign change, for a change in concavity, to see if we have an actual inflection point. All this information we're still going to use. This still holds. We're just going to expand on it. And we're going to work with rational functions, meaning we're going to allow ourselves to have x's in the denominator. Now, when you do that, you restrict the domain, right? You introduce the possibility that you might divide by 0. So the first thing we have to make sure is that we find the domain of the function and determine if there are any vertical asymptotes. So the vertical asymptotes, those usually happen where we at values of x that would cause us to divide by 0. We'll find intercepts of a graph. This we've already did. This we did in part 1. You know, if it's sort of convenient, you know, if 0's in the domain, you can always find the y-intercept. You just plug in 0. And then depending on what the function looks like and the algebra involved, it could be pretty convenient, not too much work to get x-intercepts, or if they exist. And then find the first and second derivative, get the relevant information. That's exactly what we did in the last example, or in the last section. You know, find the derivatives, make the sign charts, you know, kind of organize that information. So both items 2 and 3 we did in the last section. So that's not new. What's new is the fact that we have to actually find the domain, because it's not always going to be all real numbers. It might still happen that it's all real numbers, but it's a question. So this is new. Item 4 is new. So, you know, with polynomials, the end behavior of the graph, you know, what happens as x gets huge in either the positive or negative direction, is that we know that the graph just continues up or continues down. But now, you know, that's not always going to be the case. So to determine the end behavior of the graph, what we're going to do is calculate the limit. We're going to find the limit of the function as f becomes large. So we haven't done limits in a little while, but we're going to find the limit as x approaches infinity of the function f of x. If that limit is a constant, some value b, then y equals b is a horizontal asymptote, meaning it's a horizontal line that the graph just starts, you know, kind of approaches, gets closer to as x gets big. The second item we're going to talk a bit more about later, but it says if the limit as x approaches infinity of the function is mx plus b, then y equals mx plus b is a slant asymptote. So a slant asymptote is just, you know, a regular line that just doesn't have a 0 slope, right? And it'll be a line that your graph approaches. It just seems odd, you know, it probably seems odd anyway, to talk about the limit as x approaches infinity being mx plus b. Certainly if this is the case, then the limit as x approaches infinity of the function is actually infinity, right? It's actually going to grow without bound. But this just talks about the way that it gets large. And we'll talk more about this later. And then the last step is the same as the last step that we did before. Just summarize this information in a table, and then use that information to make a sketch. What we've got now is a couple of examples to work through. So let's get to it. Our first function, we're looking at the graph of y equals 8 over x squared plus 4. This is going to take a bit of space to kind of work through. So I'm actually going to do the first part up here, the first couple parts up in the top margin. The first part is, let's get the domain. The domain of the function. And we just want to look for, are we in danger of dividing by 0? Or possibly, are we in danger of taking the square root of a negative if radicals appear? Here I see I have x's in the bottom. So I have to really think about whether I'm going to divide by 0. But just note that, x squared plus 4, that what's in the denominator, x squared plus 4, is never 0. And so that means we're, in fact, not in danger of dividing by 0 here. So the domain here is all real numbers. And then the second part here, the intercepts. So the domain is all real numbers, meaning, of course, that 0 is in the domain. So we could find the y-intercept pretty easily. We're going to set x equal to 0, and when we do that, we get 8 over, 0 squared plus 4 is 4, so that's 2. That means that the point 0, 2 is the y-intercept. Now, for the x-intercept, we set y equal to 0. If we do that in this function, if we set y equal to 0, we get the equation 8 over x squared plus 4 equals 0. Now look, if you look at this equation, this fraction, 8 divided by x squared plus 4 equals 0, this never happens. I know there's no solution to this. One way, and I think the easiest way to see that this never happens, is that to understand that a fraction is 0 only when the numerator is 0. And 8 is never equal to 0. So that fraction could never be 0. Algebraically, you could see this if you first multiply, if you clear denominators, multiply both sides by x squared plus 4. That will leave you with the equation 8 equals 0, which certainly we know it never happens. So because this equation is never true, that means that there are no x-intercepts. So now let's get to the part where we're going to use some calculus. Let's do our derivative information. So our function, now I'm going to write this, I want to take the derivative, so I'm going to write this function in a power rule friendly way. If there were an x in the numerator, I would just use the quotient rule. But because the numerator is just a constant, the derivative, the first derivative at least, can be easier if we rewrite it in this way. Right, 8 times x squared plus 4 to the negative 1 power. Then y prime, the first derivative, is negative 8 times x squared plus 4 to the negative 2 power times 2x. Don't forget the chain rule there. I'm going to just simplify this. I'm going to put it back into the form of a fraction. So I've got, on top, I have a negative 16x over x squared plus 4 squared. Now, we can make a little sign chart for this that won't be too hard. It's a fraction. Now, all of the things that we did in the last time when we made the sign chart still apply here. You want it to be factored, and when we're talking about fractions, that means that we want the numerator and denominator to each be factored. And they already are, right? I've got negative 16x, that's just negative 16 times x, that'll get its own row. And then in the bottom, I have the square of x squared plus 4. This sign chart will be fairly simple to make. I'm going to have a row for negative 16x, and I'm going to have a row for just x squared plus 4 squared. I don't need to kind of, first of all, x squared plus 4 doesn't factor. It's an irreducible quadratic, but x squared plus 4 is always positive, and if you square that, that's definitely still positive. So the row itself is really easy to fill in. And then I fill in the row for the first derivative just like we would in the last section. The rules for the signs and how they interact is the same with division as it is for multiplication. So there's not really a whole lot of extra that we got to do. Just note that we have a critical value at x equals 0 because y prime, if the first derivative is 0, that only happens when the numerator is 0. And that only happens at 0. So I've got one critical value. I know that negative 16x is 0 there. It's going to be positive to the left and negative to the right. I know that the next row, the square of x squared plus 4, is always positive. Now, for y prime, you want to be careful when you fill in, especially for the critical values. The place, the negative 16x, that's in the numerator. And so that means that y prime is in fact 0 there. If it was a denominator that was 0, then y prime would be undefined. So we want to be careful about that. And then we fill in the table as usual. I'm going to refrain from making any conclusions now because I know I'm going to organize this information in my table later. But obviously we use this information to get in, to draw conclusions about increasing and decreasing and maxes and mins. Next, we're going to find the second derivative. And I'm going to use the quotient rule. Now I have an x in the top and the bottom of y prime. So when we use the quotient rule, and maybe you want to pause and set up the pieces of the quotient rule. I'm gonna not do the side work, but I am gonna kind of just talk out how I'm doing this. I know that it's all over g squared, so I've got x squared plus 4 to the 4th. If I square the square of x squared plus 4, I get x squared plus 4 to the 4th power. On top, I have g times f prime, so that's the denominator times the derivative of the top. The derivative of negative 16x is negative 16. So that's g times f prime minus f, which is negative 16x times g prime. Taking the derivative of the bottom, I have 2 times x squared plus 4 to the first power times 2x. Now I'm going to simplify this because that's certainly not anything I'm eager to make a sign chart of right now. We definitely need to do some simplifying. I'm going to do a couple of things here. I guess for starters, right off, I'm just going to say that's a plus. We're subtracting a negative. And then I'm going to identify common factors. So we could certainly take out a 16. And we can also take out an x squared plus 4. So if I take these out, then for this first part, for the first part of the numerator, the stuff in this box, I'm going to have to grab the negative and an x squared plus 4, because this is squared here, and I just took out the first power. Bring down this plus. And I took out the 16 and the x squared plus 4, so we just need, to get the rest of this, we just need an x times 2 and a 2 times x, so that's a 4x squared. We're going to do some simplifying here. For starters, we could cancel a common factor of x squared plus 4. Oh, which I kind of, I guess, jumped the gun on that here a little bit. That should be a 4th power, but we're going to cancel, so that'll end up being a 3rd power. And if we distribute this negative up here in the parentheses, we have a minus x squared minus 4. So combining like terms, we get a 3x squared minus 4. So this is our second derivative in a factored form. Now, the x squared plus 4 on the bottom is still irreducible. It doesn't factor, but that's fine. We know it's always positive. 3x squared minus 4, that doesn't really factor because its roots are irrational, but it does have real roots, you know, like places where it's 0. So if we want to find where the second derivative is equal to 0, well, that's only going to happen when this factor here is equal to 0, the 3x squared minus 4. And so this means that 3x squared is equal to 4, that x squared is 4/3. And taking the square root, now I'm taking a square root, so I need to consider both positive and negative roots here. X is plus or minus, if we take a square root, we'll get 2 over root 3. So there it is as an exact value. But if you throw this in the calculator, and I'm going to approximate because, you know, we're doing this so that we can plot some points, and I don't have a good sense of where 2 over root 3 is, but if I plug it in the calculator, I get about 1.15, and that'll be useful to us. All right, so now we have these two spots where the second derivative is 0. I'm only making a single row here, right? This is a very simple sign chart to make because 16 is always positive. I don't need a row for that. The bottom, x squared plus 4 cubed, is always positive. I don't need a row for that. The sign for y double prime is determined entirely by this highlighted factor, 3x squared minus 4. And I know that's 0 at those two spots. If I plug in something in between, like if I plugged in 0, I'd get a negative, and if I plug in something outside of those two values, it'll give me a positive. You could sort of check that on the calculator, but I think you'll confirm that conclusion. Now, we've got both of our derivatives. We've made these little sign charts. So I'm going to go ahead and find the y coordinates for these values. You know, the places where the second derivative is 0, those are possible inflection points. I think we can conclude just looking at the sign chart that those are actual inflection points. So I'm going to cross that out. And I'm going to just find the y coordinates. So I've got one at negative 2 over root 3, and where x is positive 2 over root 3. I'm going to put this in the calculator. Let me open that up. So we're plugging 2 over root 3 and negative 2 over root 3 in the original function. Now look up here in the original function, the only place x appears is where it's squared. So it'll actually give the same value for 2 over root 3 and negative 2 over root 3 because we're squaring it. And we get 1.5 or 3/2 for both of those. Okay, now let's organize all this information into a table. I'm going to zoom out a little bit just to kind of give myself some space. Now, our points of interest, the critical value and these two inflection point values, are at negative 2 over root 3, 0, and positive 2 over root 3. I'm going to use those three values to cut up the real number line here. Okay, now at this first column for y, we only fill that out when for the individual values of x, not for the intervals. So that'll be at negative 2 over root 3 and positive 2 over root 3, where we've already determined that the y coordinate is 3/2. And also at 0, where we've already found that coordinate right at the beginning when we were finding our intercepts. Has a y-intercept of 2. The first derivative column, we're just going to put this information down in there. So it is positive up until we get to 0, at which point 0, and then it's negative everywhere else. The second derivative is 0 at negative 2 over root 3 and positive 2 over root 3. It is positive on either side of those two, and then negative in between. And then we just write down our conclusions here. So in the first row, it's increasing, concave up. The second, at the value negative 2 over root 3, it is increasing, and we have an inflection point. The next row, between negative 2 over root 3 and 0, it's increasing, concave down. At 0, we have a maximum. Right, it's concave down at a critical value. In the next interval, it is decreasing, concave down. Then we have another inflection point, and at the same time it's decreasing because the first derivative is negative. And in our last interval here, it is decreasing and concave up. Okay, so now we have two more things to do. Before we we're going to sketch the graph, but before we do that, we need that behavior as x becomes large. That end behavior. This is a new piece in this section. What we usually call item 4, and I guess this was item 5. I just sort of skipped over 4, but it's not crucial that we do 4 before 5 because we don't really necessarily list that end behavior in the table. So we want our behavior as x approaches infinity. So we're going to find the limit as x approaches infinity of the function itself, which is 8 over x squared plus 4. Now as x gets huge, the whole denominator gets huge. So we have a fixed numerator. The numerator stays at 8, and the denominator is just growing without bound. So that means overall this fraction has to approach infinity. And that means since it approaches a constant, in this case it's 0, that means that y equals 0, the x-axis is a horizontal asymptote. All right, so now we're ready to sketch this function. We start with our anchor points, right? So we know that 0, 2 is the y-intercept. We know that is a maximum. And also, you know, we could do a little bit of analysis first. You'll notice when I put these axes down, I didn't really allow for any space below the x-axis. And that's because if you look at this function here, I've got 8, which is positive, divided by x squared plus 4, which we've already observed is always positive. So the whole graph has to only exist above the y-axis. Not only that, we know that as x gets big, that makes the denominator bigger and the function smaller. So this maximum we found at the y-intercept is actually going to be an absolute maximum. There's not going to be any value of the graph anywhere that's bigger than that. Our other anchor points are at these inflection points. And those inflection points, the x-coordinates are a little bit more than 1.15 approximately, and the y-coordinate at 3/2. So that'd be like maybe about there, maybe about there. So now let's see what happens. If we look at this, at our conclusions, right? It starts out, let's start at the way negative. It starts out increasing, concave up, and then it gets to that inflection point and becomes concave down, but still increasing. So we're increasing in a concave up fashion. We get to this inflection point and we have to turn concave down, which actually helps us because that's how we kind of head into that maximum. Then we head out of the max into that, we're still concave down into the inflection point, and then it's still decreasing, but in a concave up fashion. And now we get to where we need this information about the end behavior. The x-axis is a horizontal asymptote. That means that as x continues to get big, the graph just keeps getting closer and closer to the x-axis. That also happens as x gets large in the negative direction. If you let x approach negative infinity, that limit calculation is the same. And so it looks something like this. All right, we're going to do one more example of these curve sketching problems. We're going to sketch a graph of the curve x plus 4 over x. And let's start again. I'm gonna kind of do some of this in the top margin just because it takes a bit of space to kind of get everything done. But our first question is about the domain. And just looking at that function, we can tell we are in danger of dividing by 0, and that would happen only when x is equal to 0. So we know that x cannot equal 0. And because a value of x equal to 0 would cause us to divide by 0, that means that we have a vertical asymptote. Vertical asymptote at the line x equals 0. That's the y-axis. Our next stop is to find the intercepts. Now, 0 is not in the domain, and that means there's no y-intercept. For the x-intercept, we're going to set y equal to 0. When we do that, our equation looks like 0 equals x plus 4 over x. It's an equation with fractions. Let's clear denominators. I'm going to multiply both sides by x. And when we do that, we get 0 equals, and if we distribute, we get x squared plus 4. X squared plus 4 is always positive, right? X squared will be at least as big as 0, and then we're adding 4. So this never happens. And so that means that there is no x-intercept. So we know that there's no y-intercept, there's no x-intercept. The graph of this function never crosses either of the axes. All right, let's move on to the next thing, our derivative information. I'm going to rewrite the function to make it simpler to differentiate. So I'm going to write this as x plus 4 times x to the minus 1. Now it's just a simple power rule problem. No product or quotient rule, not even a chain rule is involved here. So y prime is 1 minus 4x to the minus 2. Now, taking a look at how y prime is written right here, if we're going to make a sign chart, we're actually going to do some algebra and rewrite it, put it back in the form of a fraction. I'm going to do that up here. So this would be 1 minus 4 over x squared. And if we get a common denominator, right, so this is 1 over 1, and if we multiply top and the bottom by x squared, we can rewrite this as x squared minus 4 all over x squared. And that will factor, the top will factor. So we have x plus 2, x minus 2, it's a nice difference of squares, all over x squared. That makes it easier, to, having it in that form. We needed to put it back in the form of a fraction, do some algebra, so that we end up with something that we can make a nice sign chart for. And we're going to do that in just a moment. I do want to just point out, though, when we go to take the second derivative, we have these two different forms for y prime, right? We have the form right here that we started with, and we have this form here. The form on the right, that's what's conducive to analysis, right, to making a sign chart and drawing some conclusions. But if I want to take the derivative again, I'm going to go ahead and use that form on the left, because that's what makes it easier. So let's go ahead and make this sign chart before we get our second derivative. I've got the first derivative is in a great format. Everything I've got just factors of the top, factors of the bottom. So I'm going to make a row for x plus 2, a row for x minus 2, a row for x squared, and then a row finally for y prime. The horizontal axis is a real number line, and so I need the critical values here. Critical values happen when y prime is either 0, which happens at -2 and 2, just by using the two factors, or you also get a critical value when the first derivative is undefined, so that happens at 0. So we have critical values at x equals -2, 0, and 2. I'm going to mark those values here in order. And now we can fill in this chart. X plus 2 is 0 at -2. It's negative to the left and positive to the right. X minus 2 is 0 at positive 2. It is negative to the left, positive to the right. X squared is 0 at 0, and it's positive everywhere else because it's squared. Now, for filling in this bottom row, y prime is 0 whenever the numerator is 0, so that means we have a 0 here at -2 and at 2. When x is 0, that makes the denominator 0. So it's actually undefined, and I indicate that by writing just an empty box there in the sign chart. Now we could fill in the rest of this just by using, you know, the rules of signs here. So I've got a negative, negative, positive. That means I start out positive. Between -2 and 0, positive, negative, positive. That'll make it a negative. Same on the other side, positive, negative, positive. So there's a negative. And then on for values greater than 2, it's positives all around. We could do some analysis, but I'm going to wait until we make that summary chart at the end. Let's go back over here to the left and find y double prime. Our second derivative is a positive 8 x to the minus 3, and now I could rewrite that as 8 over x cubed. So that's already a nice form for making a sign chart. The sign chart will be easy. There's no chance that y double prime will be equal to 0. You know, a fraction is 0 only when the numerator is, and 8 is never equal to 0. So we know that y double prime is never 0, and that means that there are no inflection points. We're still going to make a little sign chart because we do want to keep track of the concavity. 8 is always positive. The sign of y double prime will be determined entirely by the sign of x cubed. And so when x is 0, that makes us divide by 0, so the concavity is actually undefined. But for negative values, x cubed is negative. For positive values, x cubed is positive. And there's our sign chart for the second derivative. I'm going to kind of cut out some space here for the fourth item here. Let's look at the behavior as x becomes large, as x approaches infinity. We're going to look for some horizontal or slant asymptotes. So we're going to, in order to find the end behavior, we're going to evaluate the limit as x approaches infinity of the function itself, the original function, x plus 4 over x. Now, as x gets huge, this fraction here, 4 divided by x, approaches 0. Right, the numerator is fixed, and we just keep dividing by bigger and bigger numbers. X itself, this term, approaches infinity as x approaches infinity. So we know that this limit approaches infinity. However, that's not like the useful way to write this limit. What we're trying to do is figure out the end behavior. And yeah, it approaches infinity, but it approaches infinity the same way that x approaches infinity. Like, we're trying to figure out what pieces fall away to 0 as x gets huge. And then whatever remains, that's the behavior of the function as x, grows without bound. And so that's a bit like what we were talking about in the very beginning when I said I'll talk about this more when we have the limit is maybe not just a number, but is an expression. And in fact, in this case, a linear expression. This is a slant asymptote. That means we have a slant asymptote at the line y equals x. All right, now let's kind of just put all this together. Let's organize the information. All of the, values of interest, the x values, like, if we take the critical values, and we didn't have any possible inflection points. So the only values of interest are those 3 critical values. So we're going to cut up the real number line using the values -2, 0, and 2. So our first interval will go from -infinity to -2. Stop and see what's going on at -2. And then -2 to 0. And then stop and see what's going on at 0. Go from 0 to 2. Stop and see what's happening at 2. And then our last interval from 2 to infinity. I'm going to make a y column, a y prime column, a y double prime column, and then a column for conclusions. All right. The first column, that y column, we only fill in for the individual values. So at 2, 0, and negative 2. And if we plug in x equals, let's see, if we plug in x equals 2, then we get the value 2 plus 4 over 2, which is 2 plus 2, or 6. If we plug in negative 2, we get negative 2 plus 4 over negative 2, and that's negative 2 minus 2, which is negative 4. And I erroneously wrote 6 over here. 2 plus 2 is obviously 4. And at 0, we can't plug 0 in. 0 is not in the domain. So at negative 2, the y-coordinate is negative 4. At 2, it's 4. And at 0, the whole thing is undefined. We have a vertical asymptote. Now I'm just going to take the information from the sign charts we made and throw them in the y prime and y double prime columns. So for y prime, it's 0 at negative 2 and 2, and it's negative in between, and then positive on the other sides. For y double prime, it starts out negative and it is undefined at 0 and then becomes positive. Alright, so some conclusions now. From minus infinity to negative 2, our function is increasing, concave down. At negative 2, it's concave down at a critical value. That means that this is a maximum. From minus 2 to 0, it is decreasing, concave down. We've got our vertical asymptote at 0. From 0 to 2, it's decreasing, concave up. Now I just want to, before we go further, just note that here we have a scenario where we have a change in concavity. You know, for between negative 2 and 0, it's concave down. From 0 to 2, it's concave up. We have a change in concavity, no inflection point, and that's because we have a change in concavity on either side of like this vertical asymptote, a value that's not even in the domain of the function. At 2, let's see, we are concave up at a critical value, so that means this is a minimum. And from 2 to infinity, we are at increasing, concave up. All right. Now let's put this all together and let's sketch a graph. I'm going to zoom out for a moment just to set this up. Okay. Let's see. It doesn't look like I have to go up too high or out too far on either the x or y axes, just looking at the actual values that we have. So I'm going to go out, say, to 4 on the x. All right, and then I go up to 4 on the y-axis there. Now, before I get started, I'm going to remember at the beginning we said we had a vertical asymptote at x equals 0. Often, if we have an asymptote, we draw it in as a dotted line. That's already drawn because it's the y-axis, so I don't have to actually draw that. But we do have a slant asymptote at y equals x. So I'm just going to draw that dotted line. And we only have 2 points to plot, I think. We've got -2, -4, and 2, 4. So let's start on the negative side here. We know that -2, -4 is a maximum. That's what a maximum looks like. I know that it's increasing concave down as it's concave down for all the negative values, increasing concave down heading into that maximum. And then this is a slant asymptote. The slant asymptote is the end behavior. So as x gets large in the negative direction, the graph is just going to get closer and closer to that line. From -2 to 0, it's concave down decreasing. And when a graph gets close to a vertical asymptote, it can do one of two things. It can either shoot upward to infinity or shoot downward to negative infinity. This is decreasing, so it's going to shoot downward. So we have that kind of behavior on that side. For the positive x values, I'm going to scroll back up here. This is a minimum, right? At 2, 4, that's what a minimum looks like. I know that it is concave up for all the positive values. It is decreasing concave up, so that from 0 to 2. So that means this part of the graph looks like this, right? As the graph gets close to, approaches the vertical asymptote, it's got to be shooting upward. That's the only way. It's decreasing out of positive infinity into that minimum. And then it turns around. This is a minimum. It maintains its concave up behavior and is increasing, but approaching that slant asymptote. And so that's, there we go. There's sort of a picture of, a decent sketch of this graph. We did it only by plotting 2 points. I think that's worth observing. We plotted only 2 points and used the information we got from derivatives and end behavior, taking that limit to fill in the rest of what we know is going on with this graph.